Welcome back to our last video on dealing with vectors. So in our last lesson, we took a look at adding vectors at right angles, and we saw that it was basically just using Pythagorean theorem and SOHCAHTOA. And then we took a look at breaking vectors into their vertical and horizontal components. So basically the same thing, but kind of backwards. Today we're going to look at adding any two vectors. There is another way to do this, and you may have seen it in grade 11 math, depending on who your teacher was and what they felt like doing at the time. But I'm going to ask that you use the method that I'm showing you in this lesson as the way that you do it to avoid confusion on the tests. So the rules that we have are actually pretty simple. There's just three things to do. Basically, we take our vectors and we break them down into their vertical and horizontal components separately. Then we put together the verticals and the horizontals as two separate things. We basically treat them like they're parallel vectors. And then once we're done that, we put those together so we have one vertical vector and one horizontal vector, and then we find the resultant in the middle. So let's just jump in and try one. And again, when we're doing these, I'm going to recommend that you kind of think about how you're drawing them before you start drawing them. I will also point out that I believe your handout for this is a single page with no space to write. And that's because these can take up quite a bit of space and I didn't want to limit it. So you're probably going to want to do these on a separate sheet of paper, just so I didn't have to have you print out 4 sheets of paper that each had one line on them. Anyway, our first one, we have G is 35 meters north 17 degrees east. And H is 22 meters, a little bit shorter, east 41 degrees south. So our first one's mostly north, a little east, and then mostly east, a little south. So I'm going to draw them so they look kind of like this. And I'm going to draw them relatively large so that it's not too hard to see what's going on. And this one here is going to be 35. And the angle there is going to be 17 degrees. And then our second vector is going east and south, so something like this. It's a little bit shorter than the original. And the angle is relative to east is 41 degrees. So it looks something like that. And what we're ultimately looking for is a vector that starts here and ends there. And I'll call that vector R for resultant vector. Technically it's G plus H, but just so that we have one variable for the Pythagorean theorem and all that stuff, when we finally get to that point, we'll do it that way. Now what I'm going to do is I'm going to actually switch to another color here. Let's do green, I guess. And instead of thinking this as a non-right angled triangle, what I'm going to do is think of it as one right angled triangle here and a second right angled triangle here. And I can give these 4 vectors whatever names I like, whichever names I think are appropriate. Just to change it up a little bit from what we did in the last lesson, this first vector, the 35, was G. So I think I'm going to call this GV for G vertical and GH for G horizontal. And similarly, I'll call this one H horizontal and H vertical. But again, you could call them A, B, C, D, call them whatever you like. It doesn't really matter. They're just placeholders to get us to the end. Alrighty, from there, what we'll do is we'll figure out each of the components. So basically we're breaking G into its vertical and horizontal components and H into its vertical and horizontal components. And that's going to require 4 calculations. I'm going to just do this a little bit quick. If you refer back to the last lesson, if you get confused by what I'm doing here, because I'm going to take a shortcut, just refer back to the last lesson and I think you'll see what I'm setting up here. For G vertical, we'll notice that that's the adjacent and hypotenuse would be cos. So it turns out that G vertical is going to be 35 cos 17 degrees. Now really that's cos of 17 degrees equals G vertical over 35. I've just already done the little quick rearrangement to get it by itself. And 35 times the cos of 17 is 33.5, give or take. We'll have a little bit of rounding error here, but not enough to worry about. Similarly, G horizontal is the opposite to 17. That's going to be the sine one. So G horizontal will be 35 sine 17 after I've done a quick rearrangement. And that, when I throw it into the calculator, is 10.2. Okay, similarly for the H horizontal and vertical, H horizontal is the adjacent, that'll be the cos. So that'll be 22 cos 41. And that gives me 16.6. And H vertical is an opposite, so that's going to be 22 sine 41. And that'll give me 14.4. Okay, so now that I have those four pieces, what I can really think of is this line right here. Let me switch back and do this one in, let's pick a new color. Purple looks nice. We're going to think of this as a overall horizontal piece, but if I look up, that horizontal piece is going to be the horizontal part of G plus the horizontal part of H added together. So that's going to be 30, oh wait, I want to make sure I get the horizontal. That'll be 10.2 plus 16.6. Those are the two horizontal pieces. So really quick, 10.2 plus 16.6. Why am I using a calculator? That's going to be 26.8. So that's the total distance across there. And then my total vertical piece is going to be this part right here, GV, minus HV, because GV is going north and HV is going south. So that's going to give me 33.5 minus 14.4. And that gives me 19.1. So my overall here is 19.1 north. Now that I have that, just give me a second, I'm going to get rid of some of this excess highlighting. We really are looking for this one, given these two pieces, and we're back down to just adding right-angled vectors so we can figure out what the magnitude and the angle here is. All right, so to get the magnitude, r squared equals 26.8 squared plus 19.1 squared. I'll quickly throw that into my calculator. That gives me a number a little over 1,000, and then I take the square root and I get 32.9, which looks about right. And then similarly, I can set up my tan of theta equals the opposite, which is 19.1, divided by the adjacent, which is 26.8. And when I throw that into the calculator, I get down just over 35 degrees. At least to the nearest degree, it's 35. And so finally, my value for R is 32.9 meters. And the direction is east, 35 degrees north. Now, you'll notice when I drew this, I'm going to go back to refer to the colors. So we originally drew the two blue arrows, which were the two arrows given to the question, G and H. Red is the resultant arrow that we're looking for. And then I just broke everything into vertical and horizontal pieces with the green. And I want you to notice that I could have actually, I'm going to make a mess here, but I'll do it anyway. I could have drawn the first vector this way and the second one that way, and then gone down and over. The only problem with that is that I start crossing lines all over the place and it starts making a big mess. So it's usually a good idea, if you can, to just basically work the way around the outside so that you almost have, in the end, what looks like a rectangle with a triangle inside of it. The green and the purple together make a total rectangle. Horizontal top and bottom of the same length and vertical sides of the same length, and then a triangle in the center of that. So if you can, kind of work around the outside. And if there's any problems, well, there is one other way you can do this. And we're going to try this way in question 2. You can use whichever method on the test that you prefer. I like drawing the picture, but I also have more experience doing this, so I don't know. That's just my preference. But we can do it in a slightly easier way. Easier for the drawing and calculation of the pieces, a little bit less representative of what's really happening. But let's see what happens if I do this. Here we've got two vectors, 70 kilometers north 25 east and 80 kilometers east 15 north. What I'm going to do is just kind of side by side draw these vectors separately, and I'm not going to add them together. I'm not going to show them adding tip to tail, and I'm not going to draw a resultant vector because I'm just going to treat them as two separate pieces. So the first one is 70 kilometers north a little east. And I can break that down into pieces that look like this, up and over. This is 70. That angle there is 25. And then completely separately over beside it, I'm going to draw 80 kilometers east, 15 degrees north, so something that looks like this. And it'll have a piece that goes this way and a piece that goes that way. So basically, this is exactly what we did in the last lesson. We're just doing it twice in the same problem. So I'm going to call these, this time, you know what, let's call them A, B, C, and D, because it doesn't really matter what we call them. And I want to calculate each of those. So again, I'm going to use that little trick of rearranging quickly. A is adjacent to 25 degrees. So I'm going to just say that A is 70 cos 25 degrees. 70 times the cos of 25 is 63.4. And B is opposite, so it's going to be 70 sine 25. And that gives us 29.6. And again, I'm going to just quickly look at it and make sure that that at least kind of makes sense. A should be the longer one, B should be the shorter one, and worst case scenario, we got them backwards. We still have the right two numbers. It's just we reversed A and B. Likewise, I'm going to go over the second one and say that C is going to be adjacent, so that's going to be 80 cos 15 degrees. 80 times 15 cos is 77.3, which makes sense. It's almost 80, and the hypotenuse and the longest leg are very close to each other. And similarly, D is 80 sine 15 degrees. And that gives me 20.7. Okay, now what I'm going to do is put those together to see what's actually going on. So it doesn't matter whether you start with the vertical or the horizontal. I think I'm going to start with the horizontal and say that if I put these pieces together, I should get B plus C going both to the east. So B plus C should be two vectors going to the east. So 29.6 plus 77.3 is 106.9. And similarly, I look at my vectors A and D. A is going north, D is going also north, which means that I'm going to add those two together. So A and D will give me a total of 84.1 north. All right, and then I just do what I would do the other day in the last lesson and say this is my resultant vector. This is my angle theta, and then we'll use Pythagorean theorem and SOHCAHTOA. So r squared equals 106.9 squared plus 84.1 squared, which I'm definitely not doing in my head. And I'm getting 136.0. If you don't put the 0 there, that's not a big deal. Similarly to find theta, I'm going to do tan theta equals opposite, which is 84.1, over adjacent, which is 106.9. And 84.1 divided by 106.9, and then inverse tan, and that gives me 38 degrees. All right, so that means that when I put this all together, my final resultant vector is equal to 136 kilometers, and the direction is going to be east 38 degrees north. Now, one advantage this method has over the last one is sometimes if our vectors, say for instance, they're both going east, but one's going a bit north and one's going a bit south, and it's really hard to judge whether it's more north or more south, your diagram can be really wonky if you try and draw them like we did in question 1 with them together. Like this one was pretty obvious. We're going much more north than we were south, so we know the overall is north. But if we are like maybe going 10 north and 11 south, we don't know those numbers until we've drawn the picture. Then it can be kind of wonky because it should be going south, but it looks like it's going north, and it gets a little confusing. So drawing them separately can be helpful. Whichever method you choose is fine by me, as long as you're doing it by breaking them into components and not using any different methods, specifically cosine and sine laws type stuff. Even though we did that, we're not going to do vectors that way. It makes things a little bit more confusing. So break the two vectors into components, do the things that are parallel, put them together, the verticals and the horizontals, build a right-angled triangle and solve it. Let's try a couple more. Okay, this one here, B, 13 kilometers east 40 north plus 18 kilometers south 20 east. Let's just see what this would look like if we tried to draw it as one. So the first one is east and a bit north, so it's going to look something like that. And that's 13. And then we go south 20 east. That one's a little bit longer. 20 degrees there, 40 degrees there. Now, before you start drawing all this, I just want to show you, if I do this in green again, if we try to follow what's there, it would be that plus that plus that plus that, which is a little bit messy to label. So it would be better to go around the outside in this case, even though our angles aren't there. Because we can work with angles that we do have. So for instance, we can either say that this is 40 degrees or this is 50 degrees. And it doesn't matter which one of those you use. It'll change the cos and the sine, but it will give you the same two correct angles. And likewise, I'm going to make this 18 a little higher so it doesn't get confused with the angle. That's 20 degrees, or this is 70 degrees. And yeah. Okay, so now let's label these. And again, I'll just choose A, B, C, and D because it's easy. And just so it doesn't get too confusing, I'm going to pick one angle in each triangle to work with, just so that we know which one when we're talking about opposite adjacent, because it's relative to the angle given. So I'm going to use 50 in the left triangle and 70 in the right triangle. Now, I'm going to point out that I drew them touching each other, but there's no reason you couldn't have drawn basically this exact same diagram with a space in the middle and just done the left arrow and the right arrow separately, you'd still get the same A, B, C, and D, and we'd still be able to put it back together into the same picture. Okay, so we're looking for a resultant vector that starts here and ends there. And we're going to end up breaking it into components that go down and over. And I think I'll just take a moment to point out that if you think about these 4 colors as 4 different paths, all of those 4 paths start at the same place and end at the same place, which means they're all equivalent. If you were walking them, yeah, it would be longer, but if 4 friends all took different paths, started in the same place and ended in the same place, you'd all say you took the same basic trip, even though some of you might be more tired. You still started at the same place, ended at the same place. Okay, so let's break this down then. We'll call that the resultant vector. And then I can call these whatever I want. I'll call that one X and that one Y. And I think in the last question, we didn't even call them anything. We just took the numbers and added them together. Either way, really quickly defined A, B, C, and D. A is adjacent to 50, so it's going to be 13 cos 50 degrees. And in our calculator, that gives us 8.4. And then B is opposite, so it'll be 13 sine 50 degrees. And that's 9.96, which actually rounds off to 10.0 if we're keeping 1 decimal place at each of these. And looking at the picture, yeah, B should be a little longer than A. Now for C, we're going to do 18 cos 70, since we're dealing with an adjacent. That gives us 6.2. And D equals 18 sine 70, since we're dealing with an opposite. And that gives us 16.9. And sure enough, D is much longer than C, which the diagram would suggest. Okay, so now overall, the length of X is going to be equal. Just write it down over here, I guess. Actually, put it at the bottom. X is going to be the length of B plus C. So B was 10, C was 6.2. That gives us 16.2. Y, the length of Y, is going to be D minus A. Since D is long, like you'll notice that Y is south, D is a long distance south, A is a short distance north. So D minus A should give us the length of Y. And that's 16.9 minus 8.4, which is almost half as long. Yeah, actually A and Y look very close in length to each other, except opposite directions. So yeah, 8.5, and it is heading to the south. So now that we have the lengths of X and Y, we can just do R squared equals 16.2 squared plus 8.5 squared. Throw that into your calculator quick. Take the square root, and we get 18.3, which sounds about right. Just looking at the diagram. And likewise, we need to find an angle. Now, in this diagram, this is the theta we want. Even though it's a bigger angle than the bottom corner, we're trying to find the angle that we head in from our starting point, not that we arrive at our ending point. So we always do the angle relative to starting position. Okay, so that means that tan of theta will equal opposite over adjacent, or X over Y. So 16.2 over 8.5. 16.2 divided by 8.5 is almost 2, and then inverse tan gives us 62 degrees. All right, so finally we can say that our resultant vector is 18.3 kilometers, and the direction is south, 62 degrees east. Or you could also use our notation, which would be to pick the shorter one, or the more direct one, I should say, since this is mostly east and just a little south. This would be east 28 degrees south. But on a test, unless I told you specifically to do one or the other, either of those is perfectly acceptable. All right, I just want to do one more, and I think you'll immediately see what's different about this one compared to the others. Now, I don't want you to start drawing as I start drawing, because I'm going to erase my drawing, I think, relatively quickly. But this one is 65 kilometers west, 25 south. So it's going to do something like that, plus 95 kilometers north, 15 west. So that's going to be a longer one this way. 95, 15 degrees, plus, see, this is why I should have thought about this more. North 40 degrees east. So it's going to do something like that. And it's 35 kilometers and, oh, sorry, that should be north 40 degrees east, so that's 40 degrees. Okay, ultimately, when we finish doing all this, we're basically going to say we're going to start here and end there. And I'm just looking at this picture and saying roughly that one looks a little longer than the 95s. I'm going to guess it's like 100-ish. And it looks mostly north and a little bit west, but I'm not sure exactly how much. So I'm just going to just write up here really quick. My guess from the picture is approximately 100 kilometers north. If I'm just looking at the picture, I'm going to say about 30 degrees west. But that really, really is a guess. I have no idea that that's going to be accurate. Either way, I think what you're going to see is if I tried to put now on all those other lines, we'd have to go down and over, over and up and over, and then end up with an over and down. And I realize that's a horrible mess, especially since I went through the original question. But this one, I think it's easier when we're adding more than two vectors, especially to just do the separate triangles. Don't worry about putting them together in a single picture. Sometimes it's easier to see what we're looking for, but ultimately it doesn't matter as long as we put the pieces together at the end. Okay, so let's treat this as three separate triangles then. The first one, west 25 south. Looks like that. The second one, north 15 west. And that one's 95. And the third one over here is going to be north 40 east. So something like that. The fact that they're not touching and they're not attached head to tail really doesn't make any difference. We're still going to do it the exact same way. We're going to break this one into a component that goes that way and that way. This one that goes up and over. And this one that goes up and over. And then we'll give each of the sides names. I'll call this A, B, C, D, E, and F. But again, really doesn't matter what you call them. So then we can go super quick. B is going to be 65 coast 25. I'm just going to set them up and then I'll pull out the calculator in a second and save us a little bit of time. A is 65 sine 25. For this one, C is the opposite, so that's going to be 95 sine 15. And D will be 95 cos 15 since it's adjacent. And the last two, E is going to be adjacent, so that's going to be 35 cos 40. And F's going to be 35 sine 40. Okay, I'm going to pause this and write the answers in to save you a little bit of time, waiting for me to use my calculator. Okay, and there we go. I've written in the 6 components for A, B, C, D, E, and F. All right, now the thing we have to do is figure out whether overall we're going east or west and north or south. So from our guess, it looked like we were going west, but now that I'm looking at it, we're going that much west, and that much east. Yeah, I still think we're going a little bit west. But either way, if I take a look at those, I'm assuming we're going west by doing B plus C. Those are both westerly ones. And then I'm going to subtract F and see what happens. So if I actually go and draw a new diagram here, try to do this with a little bit of space. I don't want to take what we have off the screen. Our resultant vector is going to be definitely north and I think west. So I'm going to draw it like this. And the resultant vector will start here and end there. And I'm going to call this X and Y. And we're going to need a theta down there. That's our starting point. So first of all, X looking like it's going to the west is going to be B plus C minus F, which is 58.9 plus 24.6 minus 22.5, which I think is 61 even, but let me just double check quick. 58.9 plus 24.6 minus 22.5 is 61. And then I'm running out of room here, but we'll try and fit it all in. Or am I running out? No, I have more room there. I just want to leave it on the screen. Okay, so Y is going north. So that's going to be D plus E, since D is north, E is north, and subtract A. So D plus E minus A. That's 91.8 plus 26.8 minus 24.5. All right, 91.8 plus 26.8 minus 24.5 is 94.1. Okay, finally, I should have put the little arrow over the R there since it's a vector. The magnitude of R is x squared, 61 squared, plus 94.1 squared. 61 squared plus 94.1 squared equals a big number. Square rooted is 112.1 to be more precise. And similarly, the tan of theta is going to be x over y. So that's 61 over 94.1. 61 over 94.1 inverse tan gives us 33 degrees, 32.9, so 33 degrees. So finally, we can say that the resultant vector is 112.1, and the units were kilometers. And the direction is north 33 degrees west, since our drawing made it look west. Now, incidentally, if I'd been wrong about the arrows going west and I did the B plus C minus F for X, if I got a negative number, that's okay. It just means that my vector was actually going east, because I was assuming it was going west and got a negative. It can happen. It doesn't happen very often, but it can happen depending on how the diagram actually works out. Okay, so 112.1 north 33 west, and our guess was 100 north 30 degrees west. Okay, so when we drew it by hand and just kind of estimated, we got a decent guess out of it. Um, but if you want to do the math, I think it's actually easier just to do it as three separate triangles instead of trying to do it as one giant diagram. But whatever method you like, I'd recommend trying at least one of each when you're doing the practice problems. So there's a few examples here. You can do 5 of them. You choose which method you want to use. But like I said, I would try doing it as one big picture for one of them and doing it as separate triangles for one of them so that you at least have a better idea of which one you are more comfortable with. So try those practice problems, check the answers. If you're getting them right, fantastic. There may be some rounding error in both the angles and the lengths, so don't worry too much if you're just a little wee bit off. If something's coming out backwards or weird, check to see that it's not just you've reversed the two components. So a pretty common thing to do in these is to just mess up which one is cos and which one is sine. So double check to make sure that it makes sense and it looks right on your diagram, that the long one looks like the long vector and the short one looks like the short vector. And yeah, now, once you've double checked it, if you can't find out what you're doing incorrectly, by all means, feel free to contact me and I'll see what I can do to help. But good luck, and I'd say I'd see you in the next lesson, but the next lesson for you will be the practice test and then the test itself. This one's going to be a relatively short one. There aren't really a lot of skills in the end. The first day, the first lesson was mostly just talking about how vectors work, which is going to be incorporated into the other things. Basically, you're going to have to add vectors at right angles, decompose them, and then put both those together to find the addition of vectors at odd angles. You also need to know how to find directions, but if you can do the questions in this last lesson, you can do everything that we required to do in this unit. All right, good luck on the test, and I will see you in the next unit.